When dealing with a closed volume, the surface area vectors always point toward the outside of the volume. Let's calculate the gravitational flux of this gravitational field through the left-hand side of this cube. Since our system is a closed surface, the area vector must point toward the outside of the cube, and thus for the left-hand side of the cube points in the negative y-axis direction. The magnitude of the area vector is the area of a rectangle with sides dx and dz. Substitution of this area vector into the equation for gravitational flux gives us the following expression. Only the y-axis component of the gravitational field survives the dot product with the area vector. The integrals along the x-axis and z-axis of the surface can be treated separately. These integrals are straightforward and give this result. Since the gravitational field is constant, the magnitude of the gravitational flux is equal to the product of the area of the surface and the component of the gravitational field perpendicular to that surface. The negative sign indicates that the gravitational field and surface area vectors point in opposite directions. In other words, the gravitational field is pointing into the cube at this surface. Next, let's calculate the electric flux of this electric field through the top side of this cube. Since our system is a closed surface, the area vector must point toward the outside of the cube, and thus for the top side of the cube points in the positive z-axis direction. The magnitude of the area vector is the area of a rectangle with sides dx and dy. Substitution of this area vector into the equation for electric flux gives us the following expression. The electric flux through this surface is thus zero, since all of the dot products in this expression are zero. In other words, there is no electric flux through the top surface, since there is no component of the electric field perpendicular to this surface. Gauss's law for gravity relates the net gravitational flux through a closed surface to the net mass enclosed by that surface. Gauss's law for electricity relates the net electric flux through a closed surface to the net electric charge enclosed by that surface. Gauss's law for magnetism states that the net magnetic flux passing through any closed surface is zero. This cylinder encloses a net electric charge. We can determine the net electric charge from the electric fluxes through the surfaces of the cylinder using Gauss's law. The net electric flux through the entire surface of the cylinder is the sum of the electric flux through each individual surface and is equal to 60 Newton meters squared per Coulomb. Substitution of this net electric flux through the surface of the cylinder into Gauss's law gives us a net electric charge of 5.31 times 10 to the minus 10th coulombs enclosed within the cylinder. It is important to emphasize that Gauss's law relates the net gravitational or electric flux through a surface to the net mass or net electric charge enclosed by that surface. We cannot determine how many objects are enclosed by the surface, or each object's mass or electric charge, or the location of the objects. We don't know how many objects are inside this cylinder, or the electric charge of each of these objects, or the location of each of these objects. We know only that the net electric charge of all objects inside the cylinder is 5.31 times 10 to the minus 10th coulombs. Similarly, if this cube contains a net mass of 5 kilograms, we can calculate the net gravitational flux through the surfaces of the cube using Gauss's law. However, knowing the net mass enclosed or the net gravitational flux does not allow us to determine the gravitational field at the surface of the cube using Gauss's law. Ampere's law relates the integral of the magnetic field around the boundary of a surface to the net electric current passing through the surface. We can determine the area vector for the surface using a right-hand rule. Curl the fingers of your right hand in the direction of the path of integration along the boundary of the surface, and the thumb of your right hand points in the direction of the associated area vector. Currents passing through a surface will be positive or negative depending upon the direction of the current and the direction of the area vector of the surface. If the current and area vector are in the same direction, the current is positive. If the current and area vector are in opposite directions, the current is negative. Consider this system of three currents passing through the surface shown in the figure. Since the direction of the path of integration along the boundary of the surface is counterclockwise, the direction of the area vector is out of the page. The 2 microamp and 4 microamp currents are therefore positive, and the 3 microamp current is negative. Applying Ampere's law gives us the following result. Ampere's law allows us to determine the value of the line integral of the magnetic field along the boundary of a surface from the currents passing through that surface. It does not allow us to determine the value of the magnetic field from these currents at any point along the boundary. This is similar to the limitation of Gauss's law for calculating the gravitational or electric field from a distribution of mass or electric charge.